Okay, guys, welcome. So today we're going to talk about logarithmic functions. Essentially what a logarithmic function, and we'll see this sort of unfold in just a few moments here. A logarithm is the inverse function of an exponential function, right? So to start off, we sort of have this relationship between logarithms and exponentials, right? So if you have the function y equals log base A of x, and I actually think I want to do some color coding here. So let's maybe say y, and we'll say base A of x. All right, now this is equivalent to saying A to the y equals x, right? So these are equivalent statements. And if you can understand this relationship, then that's understanding 95% of the battle with logarithms. So we're going to do a bunch of exercises where we have to go back and forth between these forms, and that's going to help us a lot in terms of looking at these logarithms, right? So now, again, they just give another example here. They're saying that if you have x equals 2 to the y, that's an equivalent statement or an equivalent equation to y equals log base 2 of x, right? Now, one thing that I've always sort of stressed when I teach logarithmic and exponential equations is that no matter what, the base in either form is still the base. So the base is always the base, right? So this a in the exponential form is known as the base, and this little a down here is also the base of the logarithm. So in both cases, a is still the base, right? Now, to go from, if we're talking about x here, I usually say that the thing with the log is now not with the exponent. Right? If you look at x, that's on the same side of the equal side as the log, but it's on the opposite side of the equal sign for the exponent, right? And then the opposite is true for the y, right? And then we would say the thing with the exponent is not with the log. So if you hear me refer to that, that's what we mean, right? So we're sort of talking about going back and forth between those two forms, right? And again, I stress this again, understanding this relationship is the key to logarithms. And I usually tell my students about 95% of the battle is that. Okay, so for this first section, I want to write each of these exponential equations in logarithmic form. All right, so in this first example, again, we have this 2 is the base. So I want that 2 to be the base of my logarithm, right? Now the 32 is not with the exponent because it's on the other side of the equal sign. So I want that with my log, right? And then I need an equal sign. And then the only thing I haven't used yet is the 5. And this is with the exponent. So it should not be with the log. And this is the logarithmic form of 2 to the 5th is equal to 32. All right, let's do another one. So in this second example, all right, well, what do we have? My base is 4, and that's still going to be my base. So we have log base 4. The thing that's not with my exponent is the 1 over 16, so that's with my logarithm. And the thing that's with my exponent, the -2, should not be with my log. All right, and that's the logarithmic form of this one. And for part C, same idea. My base is 1/4, because that's the thing that's getting the exponent. The 164 is not with my exponent, so that should be with my logarithm. And my 3 is with my exponent, so that should not be with my log. So that's the logarithmic form for that one. So again, this is a key part of going back and forth between logarithms, being able to go from exponential to logarithmic form. All right, and just as important is that we can go the other direction as well. So now, given a logarithm, can you convert this to exponential form? Well, the base of my logarithm is still my base. So this will be the base of the exponent. The thing that is with my log should not be with my exponent, so 125 is going to be on this side. And the thing that's not with my logarithm, so the 3 is not with the log, so that should be with my exponent. So this is the exponential form of our logarithmic equation. Now, I usually think it's easier for students to go in this direction because at the end, you should have a sentence that makes sense, right? This is a true statement because if you take 5 and you raise it to the 3rd power, you do get 125. So if you get a true statement, you know that you did it right. And if you mix these things around, then you wouldn't have a true statement. That means you have to go back and check something. Whereas in going the other direction, we're not as familiar with logs, so I think that's usually easier to mess up. All right, but let's do another one of these. So again, in part B, 6 is the base, so that's still the base of my exponent. 2 is not with my logarithm, so that should be with my exponent. And 36 is with my logarithm, so that should not be with my exponent. So then we get 6 squared is equal to 36. And of course, that's another true statement, so we know we're good there. Okay, for part C, base is still my base, so we have 1/2. And then the thing that's not with my logarithm is the 3, so that better be with my exponent. And then I have the 1/8, right, which is with my log, so that better not be with my exponent. And of course, this is, again, another true statement. Okay, so hopefully that's not too bad. And again, if you can understand going back and forth between these two forms, that's a huge part of the battle in understanding logarithms. Okay, so now in this example, we're going to write each of these logarithmic equations in exponential form. And then once we have that, we're going to solve for whatever unknown value we have. Okay, so if we have y is equal to log base 6 of 36, if we convert that to exponential form, base is still the base. My exponent is now y because that's not with my logarithm. And the thing that's with my log should not be with my exponent. All right, now to solve this, what we would need to do, now you could probably see pretty quickly that if you square 6, you get 36, but if you didn't see that right away, one thing that you can do is you could write 36 as a power of 6, right? So how do you go from 6 to 36? By using a power. you square it, right? So if you have 6 to the something equals 6 to the something, that means that those two somethings better be equal. All right, so you can get y is equal to 2 here. All right, let's look at another example. So now if we convert this to exponential form, base is still the base, so we have a 1/2. And then this is raised to the 4th power, because the thing that's not with the log should be with the exponent. And this will be equal to x. So now, of course, 1/2 to the 4th power, this would just be 1 to the 4th over 2 to the 4th. 1 to the 4th is just 1, and 2 to the 4th should give you a 16. So that's going to give me x. All right, and finally in part C, if we convert this to exponential form, we're going to get that x, base is still my base, raise that to the 2nd power, and that will give me a 32. All right, so now to get x by itself, of course, we'll square root both sides. And then we'll get that x is equal to square root of 32, which we can simplify as a 16 times a 2, and square root of 16 is 4. So we get that x is equal to 4 square root of 2. All right, now, of course, in this case, I think it was maybe mentioned at the beginning, but I didn't maybe stress on it. Here, you do not want x to be negative square root of 32, right? Because one of the constrictions here is that whatever your base is, the base has to be positive. So you do not want x to be the negative square root. You just want the positive one. Okay, so now we're going to evaluate a bunch of these different logarithms. Now, if we want to find what log base 3 of 9 is, we're going to do something similar to what we did up here for part A. All right, if you don't know something in math, many times we just call it a variable, we call it x, and then we're going to convert this to exponential form, and then we should be able to find out what x is. So this says 3 is still my base, x is now my exponent, and this is equal to 9. Well, again, same idea. This is 3 to the x, and we could say that 9 is 3 squared, so this tells us that x is equal to 2. All right, part B, very similar. We're going to say that this equals x and convert it. So this is 3 to the x is equal to 81. And of course, if we write this, if we write 81 as a power of 3, if you do 3 to the 4th, that will give you 81. All right, so this is becoming 3 to the 4th. And then, of course, that allows us to say that x is equal to 4. Okay, part C, same idea. You can say that this is equal to x. So converting this, we get 3 to the x is equal to 3. And already both sides are written as a power of 3. We just have that there's sort of a 1 hiding there. So that gives us that x is equal to 1. All right, for part D, again, we'll say that this is equal to x, and we get 3 to the x is equal to 1. All right, now if you want to write 1 as a power of a number, you need a 0 power there. So we could say here that 3 to the x is equal to 3 to the 0, so then that gives us that x is equal to 0. All right, part E, moving right along. If we say that this is equal to x, we get a 3 to the x is equal to 1 over 3. And for this, you'll just have to think about, well, what are your negative exponent rules? How do you get a 3 down below? You make it 3 to the negative first. So that tells us that x is negative 1. All right, now for part F, you need to be a little bit creative. All right, and you want to think about, well, what's another way that we could write square root of 3? Well, you can write square root of 3 by saying 3 to the 1/2. So what we're really finding is log base 3 of 3 to the 1/2 equal to x. So then once you do that, the answer comes out right away, because when you write it, you'll have 3 to the x equals 3 to the 1/2. And then that allows you right away to say that x is 1/2. So there's our answer there. Okay, so hopefully that's not too bad. Now, what we're going to do is we're going to talk about logarithmic functions and logarithmic graphs, right? And again, the whole idea is that we're going to essentially use the fact that we can convert a logarithm to an exponential, and then we can plot some points, right? Now, again, I believe I mentioned it earlier. If I didn't, I'm going to mention it now. But we said that logarithms are the inverses of exponentials. Now, if you remember, the domain of an exponential was all real numbers. So that's why you're seeing the range of a logarithm is all real numbers, because this was the domain of exponentials. And since exponentials and logarithms are inverses, the domain of the exponential became the range of the logarithm. And on the other hand, the range of an exponential is the positive real numbers. So the domain of a logarithm is the positive numbers. All right, and on a logarithm, you get these 3 points. You get 1 over a comma -1. You get 1 comma 0 and a comma 1, right? And that's because for exponentials, you had -1 comma 1 over a, 0 comma 1, and 1 comma a. And this was for exponentials. And again, because they're inverses, you're switching the x and y coordinates. So that's sort of the relationship that's happening there. Now, in order to graph one of these things, and again, it says to state the domain and range, but that's going to be the same. So I'm not going to bother. The domain would be positive numbers, range would be all real numbers. Now, to graph one of these things, the first thing we're going to do is we're going to convert this. So if we made this into an exponential, this would be 3 to the y is equal to x. All right. Now, x is by itself here. So instead of usually we would pick x values to test, we're going to test y values. So I'm going to make my y values like -2, -1, 0, 1, and 2. And then get the corresponding x values. So if my y is -2, that means that x is 3 to the -2, right? And again, this is just negative exponents. This is 1 over 3 squared, so 1 over 9. So that means that I get one coordinate, and it's at a x value of 1/9, so it's barely off the axis here, and it's at a height of -2. So we're going to get a point that's something like that. All right. For -1, we have 3 to the -1, which is 1 over 3, so just 1/3. So that means I'm a little bit farther off the y-axis here, and we're at a height of -1. All right, now when y is 0, that means we have 3 to the 0, and anything to the 0 power is just 1. So that means that when x is 1, y is 0, so we get a point here. All right, now when y is 1, we have 3 to the 1st, of course, which is just 3. So when x is 3, we're at a height of 1. And last but not least, when y is 2, we have 3 squared, which is 9. So when my x value is 9, let's see if do I have enough points here? 1, 2, 3, 4, 5, 6, 7, 8, 9. We're at a height of 2. So of course, when I connect these points, we're going to get something like this. And again, we know that the domain is all positive numbers, so we're going to sort of get this hugging the axis like this. Now, while we're here, we might as well just say, again, since your exponentials and logarithms are inverses, where's the exponential going to be? It's actually going to be what happens when you reflect over that line, y equals x, and it will look something like this. All right, so this is y equals 3 to the x, whereas this one down here is y equals log base 3 of x. All right, so that is another thing to sort of help show the demonstration. Okay, so let's do one more where we're graphing. So again, first things first, we want to convert to exponential form. So this is 1/3 to the y is equal to x. So same idea, I want to pick easy values for y to test. Right, and we did this example in a previous video, so I'll go a little bit quicker here. If you plug in y equals -2, basically the fraction will flip and we'll get 3 squared, which is 9. When y is -1, we are just going to get a +3. For y equals 0, we get 1. For y equals 1, we're going to get a 1/3. And for y equals 2, we're going to get a 1/9. All right, so what's this look like on the graph? Well, at a height of -2, we have an x value of 9. When at a height of -1, we have an x value of 3. When we have x equals 1, we have a height of 0. When x is 1/3, we have a height of 1, so something like that. And when x is 1/9, we have a height of 2. So when we connect this, we're going to get something like this. All right, and again, just for reference, if we were to plot the corresponding inverse exponential function, right, which would be 1/3 to the x is equal to y, that's when we would get this graph here. All right, so we would get something like this. All right, and I guess technically they would intersect here, but I'm not a very good drawer apparently. Let's maybe try and make that a little better. So I guess we would get something that's more like this. Okay, so that's a little better. All right, but that's the idea behind graphing these, is first convert it to exponential form and then plot the corresponding exponential equation. All right, so now this sort of summarizes what we just talked about as far as the graphs go. Of course, the domain and range switch for exponentials to logarithms, and those 3 points on the corresponding graphs basically switch your x and y components. And in each of these cases, we get something that is sort of similar to what I drew, right? So you get that one is the reflection of the other over the line y equals x. All right, so that wraps up this video on graphing logarithmic functions and logarithmic functions in general. I hope you enjoyed, and I'll see you next time.